a simple differentiation we are going to use. Okay, so first of all, let us relate the gains of two systems with feedback and without feedback. So we know that gain with feedback is AF, which is equal to A divided by 1 plus A into beta. Okay, so what we will do is we will differentiate both sides with respect to A. So differentiating on both sides with respect to A. Okay, so what do we get? On left hand side we have DAF divided by DA is equal to, okay, since here you have numerator and denominator, you will have to use UV rule. Okay, so what is UV rule? Denominator square, okay, into, I mean, on the numerator, denominator, that is 1 plus A beta into differentiation of the numerator. So you are differentiating with respect to A, right? So differentiation of A with respect to A becomes unity minus numerator into differentiation of the denominator. So differentiation of 1 plus A beta, right? So differentiation of 1 is 0 and differentiation of A beta is beta. Or if you open up the brackets, you will get A beta plus 1 minus A beta on the numerator, and on the denominator you have 1 plus A beta the whole square. So A beta gets cancelled, hence you will get change in AF, okay, with respect to change in A, that is DAF divided by DA is equal to 1 divided by 1 plus A beta the whole square. All right. Now what we will do, okay, we will divide. So dividing both sides by AF. Okay, let's divide the both sides by AF. So what do we get? When we divide both sides by AF, we get, okay, what I will do, this I will bring it to the right hand side. So I get DAF divided by AF, as I am dividing left hand side with the AF. Okay, similarly on the right hand side, okay, what do I have? I have, you know, this DA factor in the numerator divided by 1 plus A beta the whole square into 1 by AF, right? Because I have to divide on the right hand side also with the AF in order to, you know, keep the relation intact. Okay. Now here itself, what I will do, I will substitute for AF on the right hand side. Okay. So on RHS, let me write on RHS substitute. Okay. AF. What is AF? AF is A divided by 1 plus A beta. Okay. Since AF is, you know, coming in the denominator in the right hand side, so basically, you know, this relation will appear in flipped manner. So DAF by AF is equal to DA divided by 1 plus A beta the whole square into 1 by F. So you take the reciprocal of AF. So denominator gets shifted in the numerator and the numerator comes in the denominator. So what is that you are seeing here? So you are seeing the cancellation of 1 plus A beta with the denominator. So you are going to have DAF divided by AF is equal to 1 divided by, let me take this ratio, okay, separately. Okay, what is it? 1 divided by 1 plus A beta into dA by A. dA by A. Okay, so this is basically the desensitivity of the gain. Okay, where you know the left hand term, that is DAF divided by AF. Okay, so you can clearly observe that DAF, you know, you can consider it as delta AF. So which is nothing but the change in the closed loop gain, right? Changing the closed loop gain. Okay, so change divided by the original gain is considered as fractional change. Fractional change in amplification, because A is amplification with feedback. On the other hand, the right hand side term dA divided by A, okay, dA divided by A is also a fractional change, but without feedback. All right. Now the term 1 plus A beta is taken as D, and which is defined as T sensitivity. T sensitivity. Okay. So you can write DAF by AF. Always let us take the modulus, okay, because sometimes DAF you may get it as negative, provided if you subtract a bigger number from a smaller number. That's the reason, to absorb the negative sign, we always take the modulus on both sides, okay, is equal to 1 divided by, okay, 1 plus A beta. A beta, you can consider it as the desensitivity factor into dA by A. Okay, again, I have taken the mod. All right. Fine. All right. So this is about the small derivation regarding desensitivity. Okay. For short question, short notes, they can ask for 5 to 6 marks. Okay. All right. Now let us look at the problems. There are some formulas for which you will not have any derivation. So what I will do, as in when I will do the problems, I will talk about those formulas, right? So first problem, okay, it says an amplifier has a midband voltage gain of 1000.
Sir, you are muted, sir. Your microphone is off, sir.
My microphone is not off. My microphone is proper. Isn't it?
Yes, sir.
Yes, sir.
You can hear, right?
Yes, sir.
Okay. Yeah, Shailaja, tell me. You had raised your hand, so let me know what is it. Yeah, tell me, Shailaja, you had raised your hand. Okay. By mistake. All right. I don't know. Fine. So given an amplifier has a midband voltage gain of 1000. So let me directly write AV mid is equal to 1000. With FL is equal to 50 Hertz and FH is equal to 50 kilohertz. Okay. If 5% feedback is applied, so beta is equal to 5%, which is equal to 0.05. Calculate FL, FH and bandwidth with feedback. With feedback. All right. So this is the given problem. Okay. So mid-band voltage gain is given, which is 1000. FL is given and FH is given. What is FL? FL is lower cutoff frequency. Okay. And FH is equal to upper or higher cutoff frequency. Cutoff frequency. So what is this lower and upper cutoff frequency? I think I have already told you in the previous class. Okay. So basically this lower and upper cutoff frequencies, talks about the bandwidth. Okay. Let us say this is our frequency response curve. Okay. Which is plotted against, AV versus frequency. So this is the typical frequency response curve. Okay. Now, in this frequency response curve, you can see that, there's a portion in the graph which remains constant, okay, which remains constant, irrespective of the frequency variations. Okay, that portion is basically called as, the midband. Okay, so the corresponding gain is denoted as AV mid. I think the same concept you will study in network analysis also. Okay. All right. So that is your AV mid, which is the maximum, gain. Okay. So at AV mid, the amplifier exhibits the maximum possible gain. Okay. Now we will also determine 2 points. Okay, 2 points on the basis of the power delivered. Okay. So at these 2 points, the power delivered by the amplifier will be 50% to that in the midband. Okay. So that can be done by locating a point which is, let's say, 0.707 times AV mid. Remember, 1 by root 2 is 0.707. Okay. So when you calculate the value at 1 by root 2 times AV mid, you basically get a line. Okay. So this is 3 decibels, okay, minus 3 decibels in case of logarithmic scale, right? Because if you take 20 log 0.707 is minus 3 decibels, because anything less than unity gives negative decibel value. All right. So measure that 3 decibel level, okay, and then draw a straight line that will give you, 2 distinct points. Okay. The lower value is considered as FL, which is called as lower cutoff frequency, and the higher value is considered as FH, which is called as upper or higher cutoff frequencies. Okay. The difference between FH and FL is called as bandwidth. Okay. So basically, in this problem, what you are supposed to find is the lower cutoff frequency and upper cutoff frequency, as well as bandwidth for with and without feedback. Okay, with feedback and without feedback. Okay, let me write and without feedback. Okay, so with feedback, what happens is that, as I have told in the previous class, that with feedback, the gain reduces. Okay, the gain reduces, but remember one thing, even though the gain reduces, the bandwidth increases. Okay, in the sense, so gain reduces. So let me do it with a blue line. So you measure 3 dB down from here, let's say somewhere here. Okay, and then draw a line. Okay, somewhere here. Okay. So once again, this 3 dB level, okay, will give you different FH value and a different EFL value. Okay. So blue line stands for with feedback. Okay, with feedback. So as you can see, EFL becomes less as compared to EFL for a case without feedback. On the other hand, if you look at on the right hand side, FH increases, right? FH with feedback is more than FH without feedback. So due to which what happens is that the bandwidth increases. So bandwidth with feedback increases. Okay, so this is the effect of negative feedback on bandwidth. Though there is a dip in amplifier gain, but there are several other advantages. All right, fine. So first, let us consider bandwidth without feedback. Okay, let me write bandwidth without feedback. Okay, bandwidth without feedback, let us take it as BW, which is equal to FH minus EFH. Okay, so what is EFH? 50 kilohertz minus 50 hertz, right? Yeah, 50 hertz. So the difference will give you the bandwidth. That's 49.95. So bandwidth is 49.95 kilohertz. Okay. Next, let us find out bandwidth with feedback. Okay. So bandwidth with feedback, let us take it as BWEF, which is equal to bandwidth without feedback into 1 plus AV mid into beta. Okay, so this is the formula. Okay, this is the formula. So let's calculate bandwidth with feedback is equal to, without feedback, the bandwidth was 49.95 kilohertz into 1 plus AV mid. Okay, AV mid is, they have given, right, 1000 into beta. Okay, so beta is given as 5%, so it is 0.05. So that is 49.95 kilohertz into 1 plus 1000 into 0.05, that's 50. Okay, so when you multiply, you will get it as 2.54 megahertz. 2.547. Okay, so that's the bandwidth. Okay, next you need to determine the lower and upper cutoff frequencies with the feedback. So FL, F, that is lower cutoff frequency with feedback, and FHF, upper cutoff frequency with feedback. The formula is, okay, you have to take it very logically. So with bandwidth, with respect to this graph, what is that we are seeing? The lower cutoff frequency decreases, right? So in order to have a decrement in lower cutoff frequency, what you must have in your formula is that the factor should come in the denominator. So AV mid into beta will come in the denominator. On the other hand, if you look at upper cutoff frequency, the upper cutoff frequency gets increased with feedback. So that's the reason what you have to do is FH you need to multiply with the feedback factor. Sorry, the amplifier. 1 plus AV mid into beta factor. Okay. So that will give you 50 divided by 1 plus. Okay, AV mid is 1000 into 0.05. So basically it is 50 divided by 51. Okay, that is 0.98. So 0.98 hertz. Okay, you see the effect of feedback on lower cutoff frequency. Without feedback, the lower cutoff frequency value was 50 hertz. With the feedback, the 50 hertz value has reduced to just 0.98 hertz, closer to 1 hertz it is. Okay, now let us look at the effect on the upper cutoff frequency. So that's 50 kilohertz into 1 plus, again, 1000 into 0.05. So basically it is 51 times 50 kilohertz. Okay, that is 25.5. So with feedback, the upper cutoff frequency is 2.55 megahertz. Okay, you see the difference. Without frequency, the upper cutoff frequency was just 50 kilohertz. With feedback, the upper cutoff frequency has increased to 2.55 megahertz. Okay. So this is how we solve the feedback type of problems. Okay. Problem number 2, let us take up. All right. So it says, if an amplifier has a bandwidth of 300 kilohertz, and a voltage gain of 100, what will be the new bandwidth gain and gain if 10% feedback is introduced? Okay, if 10% feedback is introduced. That is the first one. Second one, what will be the gain bandwidth product before and after feedback? Third one, what should be the amount of feedback to get a bandwidth of 800 kilohertz? Okay, to get a bandwidth of 800 kilohertz. Okay. All right. So there are 3 parts. In the first part, you need to determine, bandwidth and gain if a 10% feedback is introduced. All right. Fine. So let us look at the first part. So gain with feedback is equal to A divided by 1 plus A beta. Okay. So that is equal to, what is A? A is 100. Okay. All right. You write AB 100 divided by 1 plus 100 into beta. Okay. Beta is 10%. That is 0.1. So it is 100 divided by basically 11. 11. So with feedback, the gain has reduced from 100 to 9.09. 9.09. Okay, so that's the first part. Now, second part, gain bandwidth product. Again, for the first time, we are hearing this word, right? Gain bandwidth product. So gain bandwidth product is nothing but pretty straightforward definition. It's a product of gain and bandwidth. That's all. So it is gain into bandwidth. Gain into bandwidth. Now you need to determine gain bandwidth product before and after the feedback. That means to say, with feedback, what is the gain bandwidth product, and without feedback, what is the gain bandwidth product? Okay, so first let me write without feedback. Without feedback. So without feedback, gain bandwidth product is equal to, okay, without feedback, so AV into bandwidth. Okay, AV into bandwidth. So AV we know, right? What is AV? AV is 100. Now, what is bandwidth? What is bandwidth? Remember one thing, in order to find bandwidth, either, you should be given with the straightforward value of the bandwidth, or at least you should know what are the values of FH and FL. Okay, since FH and FL values are not given, okay, but we have been given with, straightforward the bandwidth value. All right, then pretty simple. So this is 300 kilohertz. They are given directly. Okay, so no worries. So let's calculate the gain bandwidth product. Gain bandwidth without feedback is equal to AV, which is 100, into bandwidth, which is given as 300 kilohertz, into 10 to the power 3. Okay, so it is 100 into 300 kilohertz, that is 30 megahertz. Okay, 30 megahertz. Why I'm writing megahertz? Because this is unitless. Which one? The voltage gain is unitless, but the bandwidth has a unit, right? Hertz. So that's the reason the gain bandwidth product is being given with Hertz unit. Okay. Next, let us take up with feedback. With feedback. Now, with feedback, your gain bandwidth product okay, so this is with feedback. It is given as bandwidth with feedback into gain with feedback. So it is BWF into AVF, okay, is equal to, okay, what is BWF? So BWF is equal to BW into 1 plus AV times beta. Okay, so that is equal to BW is 300 kilohertz. It's already given into 1 plus AV is 100 and beta is 0.1. Okay, so you will get BWF is equal to as 3.3 megahertz. Okay, 3.3 megahertz. And AVF we have already found, right? That is 9.09. Therefore, bandwidth with feedback is 9.09 into BWF, 3.3 into 10 to the power 6. Okay, so that is 29.997 megahertz. Okay, so if you compare the two values, okay, if you compare the two values, gain bandwidth product without feedback with gain bandwidth product with feedback, you would see that the gain bandwidth remains the same, right? In the previous case, it was 30 megahertz. In the present state with feedback, the product remains 30 megahertz. So gain bandwidth product remains the same. Okay, because the feedback basically tries to keep the gain bandwidth product, the same. Okay, so that's the first part. Yeah, bandwidth and AV we have already found. Gain bandwidth is also done. The third one, beta, to get a bandwidth of 800 kilohertz. So beta to get a bandwidth of 800 kilohertz. Okay, so let us write down the formula. BWF is equal to BW into 1 plus AV into beta. So BW F they have already given, right? That is 800 kilohertz into 10 to the power 3 is equal to BW. BW in the data it is given as 300 kilohertz. So 300 into 10 to the power 3 into 1 plus AV. AV is 100 and beta is unknown. That is what we are supposed to find out. Okay, so it is 800 kilo divided by 300 kilo. Okay, minus 1 and whole thing gets divided by 100, which is beta. Okay, so how much you'll get? 800 by 300 minus 1 divided by 100. You will get 1 by 60, right? So that is 1 by 60, or beta is equal to 0.0166. Or in terms of percentage into 100 will give you 1.667%. So that's the feedback factor. Okay, all right, so that's your second problem. Okay. Third problem, an amplifier has a voltage gain of 4000. Its input impedance is 2 kilo ohm. And output impedance is 60 kilo ohm. Okay. Calculate voltage gain, input impedance, output impedance. If 5% of the feedback, if 5% of feedback is fed in the form of voltage series feedback, is fed in the form of series negative voltage feedback. Series negative voltage feedback. Okay, so if 5% of the feedback is fed something like series negative feedback. Okay, so for this, series negative feedback of 5%, you need to determine AV, RI, and R0. So since you need to determine AV, RI, and R0 in the presence of feedback, let us denote AV as AVF, RIF, and R0F. Okay. So first of all, what you have to do is you have to identify the type of feedback amplifier. So what is it? Series negative voltage feedback. So it is basically, voltage series feedback. Okay. So in case of voltage series feedback, we have seen that input resistance with feedback increases by a factor of AV into beta, and output resistance with feedback, okay, will reduce by a factor of 1 plus, AV into beta. So this is what we are supposed to find out. All right. So fine. What is RI? So without feedback, the input resistance is 2 kilo ohm into 1 plus AV into beta. What is AV? AV is 4000 into beta. Beta is 5%, so 0.05. So that will give you the input resistance as 402 kilo ohm. Okay. So from 2 kilo ohm, the input resistance has increased to 402 kilo ohm. Okay. Let's look at the output resistance with feedback. So output resistance without feedback is 60 kilo divided by 1 plus 4000 into 0.05. So R0F is equal to so 60 kilo divided by the factor will give you 298.5 ohms. Okay. So you can see the output resistance has reduced from 60 kilo ohm to just 298.5 ohms. So that is the effect of negative feedback for a voltage series feedback amplifier. Okay, so that's the first part. A, this is B. Okay, now let us find out C. So that is voltage gain with feedback is gain without feedback divided by 1 plus gain without feedback into feedback factor. So that is 4000 divided by 1 plus 4000 into 0.05. So you would get AVF is equal to 19.9. Okay, so you can observe that the closed loop gain has drastically reduced from a no load value of 4000 units to just about 20 units. Okay, so that's your third problem. Okay, fourth problem. Okay, it is given that an amplifier without feedback, so amplifier without feedback gives a fundamental output voltage of 36 volt. Okay. So without feedback, output is 36 volt. Okay. When the input is 0.028. So when the input is 0.028 volts. Okay. First one. If 1.2% of the output is fed back into the input in a negative voltage series feedback circuit, what is the output voltage? So basically 1.2% of the output is fed back to the input in a negative voltage series feedback. voltage series feedback. Okay. Then what is the output voltage? Okay. If 1.2% of the output is fed back to the input in a voltage series feedback manner, what is the output voltage? All right, so this is the problem. So you know that voltage gain is output by input. Okay, voltage gain is output by input. So I'm writing this relation with respect to without feedback. So without feedback, they have given that output voltage is 36 volts for an input voltage of 0.028. So what is the no load gain of the amplifier? So 36 divided by 0.028. Okay, that is 1285.71. 0.71. Okay. So you need to determine V naught if a feedback value of 1.2% is established. Okay. So what we will do, we will first find out AVF. Okay. That is gain with feedback. So gain with feedback is AV divided by 1 plus AV into beta. So that is, you have already found, right? AV. So 1285.71 divided by 1 plus 1285.71 into beta. Beta is 1.2%. So that is 0.012. So how much you will get? AVF as you will get it as 78.26. Okay, and therefore you can now find V naught. So AVF, once again, it is V naught by Vs. Okay, so that implies V naught is equal to AVF into Vs. Okay, we are assuming Vs is equal to Vi. So V naught is equal to AVF, that is 78.26. Okay, into Vs. Okay, Vs they have already given, right? 0.028. So that will give you an output voltage of 2.19 volts. Okay, you can clearly observe that without feedback, the output were to be at 36 volt level. Now with feedback, the output has dropped down to just 2.19 volts. All right. So that is your problem number 4. Okay, this is problem number 5. Yes, problem number 5. Okay. Okay. So it says an amplifier having a voltage gain of 20 dB uses 1/20th of its output in negative feedback. So this amplifier uses 1/20th of its output in negative feedback. All right. Calculate the gain with feedback. The percentage change in gain without and with feedback. Next, percentage change in gain so percentage change, let us take it as delta AVF. Okay. Since we have taken AF, let us define percentage change as percentage delta AF. Okay. Percentage change in gain without and with feedback. And delta AV. with a consequent on 50% change in GM. Okay, so let me read out. An amplifier having a voltage gain of 60 decibels uses 1/20th of its output in negative feedback. Okay, calculate the gain with feedback. The percentage change in gain with and without feedback, with a consequent on 50% change in GM. Okay, so for a change of GM about 50%, you know what is that? The change observed in with feedback and without feedback case. All right, fine. So first let us solve the first part. Okay, so given that amplifier gain, okay, so AV is 60 decibels. Okay, so general formula for AV is that ratio of output voltage to input voltage. Okay, but here the gain is mentioned in decibels. So therefore, in decibels, what you have to do is 20 log to the base 10 of AV. So you have to convert, you know, this absolute system into decibel system. So by taking the logarithmic on both sides. Okay, so that is equal to 60 decibels, right? So it is given as 60 decibel. Okay, or log 10 of AV is equal to 60 by 20, that is 3. That implies, okay, what you have to do is you have to take the anti-log, right? So so AV is equal to anti-log. Okay, what is the anti-log of log to the base 10? It is 10 to the power x. So this is 10 to the power. What is x? X is the right hand side term. So it is 10 to the power 3. So that is 1000. So 1000 is the gain of this particular amplifier. So therefore, the closed loop gain AF is equal to open loop gain AV divided by 1 plus AV into beta. That is open loop gain we have found 1000 divided by 1 plus 1000 into beta. Okay, so beta is 1 by 20, right? So 1/20th they have given. Okay, so 1 by 20 is nothing but 0.05. Okay, so it is 0.05. So that gives the closed loop gain of 19.6. Okay, so that's your part 1 done. Okay, now let us look at part 2. Okay, again, part 2, you know, requires some formula which we haven't discussed in the previous classes. Okay, but you know, you can do it in a qualitative manner. Okay, now in part 2, what is that you are supposed to find? You are supposed to find change in the gain with feedback and without feedback. Okay, for a variation of GM by 50%. Okay, so here the variation is 50%. Okay, variation in GM is 50%. Okay, now remember one thing. This feedback voltage VF, okay, is actually beta times V naught. Okay, so whatever variation is happening in, you know, GM. Okay, what is GM? GM is nothing but amplifier gain. Okay, in particular GM we are going to use it for a transconductance amplifier, right? Okay, it is for It is the gain of a transconductance amplifier. Now, if there is a change of 50% in the amplifier section, that 50% variation gets percolated or gets transferred to the feedback network as well. Okay, so therefore, what we can do over here is that the changing open loop gain. Okay, first let me write it as A. Okay, so changing open loop gain. Okay, what do you mean by open loop gain? Open loop gain is nothing but without feedback. Without feedback. Okay, can be given as, okay, let me write this as capital AV, which refers to the new value of AV due to the change. So, okay, let me write this as AV new is equal to AV old plus or minus change into AV old. So this is the formula. Okay. This is, you can say this is made up formula. Okay. So I only created this formula. Okay. So AV new, you want to know the new, gain without feedback. Okay. In order to find the new gain, what is that you should do? You should consider the old gain, and then you also, add and subtract the change that is taking place. Okay. Let's see how exactly we find out. So AV new is equal to AV old. What was your old voltage gain? Open loop voltage gain without feedback was 1000. So 1000 plus or minus. Okay, why plus or minus? It is mentioned that change. So change means it can be an incremental change or decremental change. So that's the reason, you have to incorporate both plus as well as minus term here. Okay. And then the change part. What is that change part? The change factor is 50%, which is nothing but 0.5 into, the old voltage gain value, which is 1000, or AV new is equal to 1000 plus or minus 500. So that gives AV new as either 1500 or 500. Okay, so basically, you can see that a change in the amplifier gain, okay, a change in amplifier gain can greatly reduce, or it can greatly affect the open loop change. Okay, open loop voltage gain. You can see that original open loop voltage gain is 1000. Now, due to the variation in GM, the new open loop gain can be either 1500 or it can be just 500. Okay, so you can say that too much variation. Okay, hence you can say no stability. Right, there is no stability. Okay, crazily it is varying the voltage gain. Now let us look at the with feedback what happens. So with feedback, what we can do is we can write down this formula. AVF new is equal to AV. Okay. Now once again, when you say AV, okay, you have to write AV new because the amplifier gain is changing. So AV new divided by 1 plus AV new into beta. Okay, which is equal to, what is AV new? AV new, we have this formula, right? So AV new can be given with this formula. So AV new is nothing but 1000 plus or minus 0.5 into 1000 divided by 1 plus 1000 plus or minus 0.5 into 1000 into 0.05, which is the feedback factor. So AVF new going to be, okay, it is 1000 plus or minus 500 divided by 1 plus 1000 plus or minus 500 into 0.05. Okay, that is equal to 19.23 or 19.73. Okay. For the same, 50% variation, if you look at the change in closed loop gain, okay, the closed loop gain variation is very, very small. Okay, 19.23 or 19.73. So there is a difference of about 0.5 units. That's all. So your closed loop gain getting varied by a factor of just 0.5 units. On the other hand, your open loop gain is varying by a factor of 1000 units. Okay, so which is better? Obviously, the closed loop system is better because it greatly stabilizes the amplifier overall amplifier gain. Okay, so you can say that closed loop system with negative feedback stabilizes the gain. Okay, stabilizes the gain. Okay, all right. So that's your problem number 5. Okay. Now let us look at, say, 6th problem. Okay. Okay. Right. So it's given that an amplifier with negative feedback has a voltage gain of 120. With negative feedback, the amplifier has a voltage gain of 120. It is found that without feedback, an input signal of 60 millivolt is required to produce a particular output. An input signal of 60 millivolt is required to produce a particular output, whereas with feedback, the input signal must be 0.5 volt. The input signal must be 0.5 volt to get the same output. Okay. Find AV and beta of the amplifier. Find AV and beta of the amplifier. Okay. Let's look at the solution. Okay, it's a very simple problem. You have been given with 2 cases, without feedback and with feedback. So without feedback, they are saying the input is 60 millivolt, and that 60 millivolt is going to give you a particular output. Okay. Now with feedback, when the input is 0.5 volt, okay, the system must produce the same output. Okay. So in order to solve this particular problem, first you need to find out what is that output which you are going to get without feedback. So let me write without feedback. Okay, so gain is given. We know that voltage gain is output voltage to the input voltage ratio, right? So that is equal to, okay, what is output voltage? We do not know. So we'll keep it V0. And what is input voltage? Input voltage is 60 millivolt, which is equal to AV. AV they have already given 120. So cross multiply, okay, you will get the value of V0, right? So, oh, sorry. An amplifier with negative feedback has a voltage gain of 120. So this should have been 120, okay? And without feedback, when the input is 60 millivolt, it gives a particular output. And with feedback, when the input is 0.5 volt, what should be the value of AV and beta to get the same output. Okay, this is AVF. So AVF is V naught by Vs. Okay, because with feedback we consider the source signal. Okay, and then with feedback. On the other hand, without feedback, AV is equal to V naught by Vi. Okay, V naught by Vi. Okay, so AVF is 120. Okay, it is given is equal to V naught divided by Vs. So with the feedback, see they have given input signal is 0.5 volt. So Vi is equal to Vs. So which is 0.5 volt. So that will give you V naught is equal to 60 volt. Okay. Now without feedback, you can find out AV. Okay, because AV is V naught divided by Vi. So without feedback, the input voltage is 60 millivolt. So it is 60 into 10 to the power minus 3, which is equal to, in the denominator, let us write 60 into 10 to the power minus 3 and V naught, because they have mentioned that in both the cases, the output remains the same. So output you have already calculated from the previous step, right? So that is 60 divided by 60 milli. So that will give you AV is equal to 1000. So the open loop gain is 1000. Okay, all right. Now you need to find out, AV is being found. Okay, now you need to find out beta. Okay, so to find out beta, let us write down the closed loop gain. AF is equal to AV divided by 1 plus AV into beta. So AF is given. So AF is 120 is equal to 1000 divided by 1 plus 1000 into beta. Okay, so you need to cross multiply. So 120 plus 120 into 1000 into beta is equal to 1000. Okay, or beta is equal to 1000 minus 120 divided by 120 into 1000. Okay, so that you will get it as 0.00733. Okay, so that is your problem number 6. Okay, all right, and the 7th problem, let us consider an amplifier with an open loop gain. Okay, AV is equal to 1000 plus or minus 100 is available. It is necessary to have an amplifier whose voltage gain varies not more than plus or minus 0.1%. It is necessary to have an amplifier whose voltage gain varies not more than plus or minus 0.1%. Okay, find beta, the reverse transmission factor beta, and gain with feedback. Okay, gain with feedback. Okay, all right. Now, since there is a mention of, change in open loop gain as well as the closed loop gain. Okay, the change in open loop gain is about 1000 plus or minus 100, and it is expected to have an amplifier, okay, whose voltage gain will not vary more than plus or minus 0.1%. So what we have to do is we have to use the sensitivity relation. Okay, other day we talked about the desensitivity factor, right? So that relation we need to taken into consideration. So desensitivity factor can be brought into picture by taking out this ratio. Okay, delta AF by AF, okay, is equal to 1 divided by 1 plus beta A into dA by A. Okay, so that is equal to okay. Now that is equal to this DAF. Okay, DAF is what? AF stands for closed loop gain, right? AF stands for closed loop gain, and DAF stands for the change in closed loop gain. So this is the one. This is delta AF or DAF. Okay, so that is 0.1%. Okay, so put together, you can say that the variation, right? So variation means you need to have some sort of division factor comes into picture. Okay, ratio. So this can be taken as DAF divided by AF, and the previous, okay, this also DAF. So the whole thing we can take it as 0.1, okay, percent. So convert it to absolute 0.1 divided by 100. Okay, so this refers to 0.1% plus or minus. Don't worry, we will take out the modulus. Okay, this refers to 0.1%, which is equal to 1 divided by 1 plus beta A into, okay, what is this dA by A? Have they mentioned in terms of percentage basis? No, they haven't mentioned in terms of percentage basis. Instead, they have mentioned in terms of, AV is equal to AV plus or minus delta AV. So this factor refers to basically delta AV, okay, which can be considered as DAV. Okay, and this is your AV. Okay, so this becomes, numerator becomes the change factor. So they have mentioned plus or minus 100. So this is the change factor divided by A. A is nothing but the given amplifier gain, which is 1000. Okay. So you need to simplify. So when you simplify, what happens? This gets cancelled, and when you cross multiply, you basically get, this is 1000, sorry. So 100, and here 10 is remaining. So this becomes 1 divided by 1 plus beta A into 100 by 10. So it is 10. Okay. And this comes in the denominator. So basically you get 1 plus beta A is equal to 100, or beta A is equal to 99. Okay. Or beta is equal to 99 divided by A. Okay. So that is 99 divided by 1000, right? Because A is 1000. So that is 0.099 or 9.9%. Okay. So having known the beta factor, you can find out AF. AF is equal to AV divided by 1 plus AV into beta. So 1000 divided by 1 plus 1000 into 0.099. Okay, that gives the closed loop gain as 10 units. Okay, so that's your problem number 7. Okay. Okay, and one last problem I will solve, which was asked in the recent examination. Okay, January 2018 it was asked. Okay, so it says the open loop gain of an amplifier is subjected to variation of 10%. So open loop gain variation is 10% due to changes in temperature. Okay. Using such an amplifier, design a feedback amplifier such that the closed loop gain of the amplifier is 450 plus or minus 1. Okay, so they are asking you to design an amplifier such that, ST means such that closed loop gain, so closed loop gain of the amplifier, okay, closed loop gain is 450 plus or minus 1%. That means to say 450 should be the gain and the maximum permissible variation is just plus or minus 1%. Okay, find the value of open loop gain of the amplifier and feedback factor. So find the value of open loop gain. So what is open loop gain and feedback factor beta? Okay, this is what you are supposed to find. Okay. Solution. So first let us write down the stability part, because 10% and 1% is being given, right? So let us first write gain stability without feedback. Gain stability without feedback. Okay, so the gain stability without feedback is 10%. So plus or minus 10%. And similarly, gain stability with the feedback is plus or minus 1%. Is plus or minus 1%. Okay. Therefore, you can write down that previous formula. DAF divided by AF is equal to 1 divided by 1 plus beta A into DAV divided by AV. Okay. Okay. Now they have already mentioned the percentage change, right? So this 10% refers to without feedback, right? So that means to say DAV by AV. And this 1% stands for DAF divided by A. You see, it is mentioned in percentage basis. So directly you can take down. So what you can do is, C is your 1% is equal to 1 divided by 1 plus beta A into the right hand side you have 10%. So even if you divide by 100, this percentage is going to get cancelled. So that means to say when you cross multiply, you get 1 plus beta A is equal to 10. Okay, 1 plus beta A is equal to 10. So therefore, the closed loop gain AF is the open loop gain divided by 1 plus A beta. Okay. Or the open loop gain A is equal to closed loop gain into 1 plus A beta, which is equal to, okay. The closed loop gain, they have already mentioned, right? The closed loop gain, okay, is given as 450. This is your closed loop gain. So it is basically 450 into 1 plus Okay, you don't have to do 1 plus because 1 plus A beta is already known to you, which is 10, right? So it is 10. Okay, so you will get it as 4,500. It is 4,500. Okay, so therefore feedback factor beta. Okay, so basically you can come. So from equation star, you can take out the feedback factor beta. Okay, so the feedback factor beta is basically 10 minus 1 divided by A. Okay, that is 9 divided by A, which is 4,500. Okay, how much you'll get? 9 by 4,500 is 2 milli minus 3. Okay, so that's the feedback factor. Okay, so that is it about from the feedback amplifier. So I have solved about 8 problems. Okay, so please go through with these problems. Okay. And the final topic is practical feedback amplifier circuits. Okay, so some examples for practical feedback amplifier circuits. Okay, so first let me consider an example for voltage series. Voltage series feedback. Okay, so for voltage series feedback, the example going to be your emitter follower. Emitter follower. Okay, so in this emitter follower, okay, you can I will first draw the circuit diagram. This is the circuit diagram of emitter follower, right? Okay, RC, I will write RC just for the sake of writing down the equations. So actually in emitter follower, this RC is basically 1, right? Because there is a short circuit here. So I'll consider negligibly small RC resistance value. Okay, you can just write very small, as good as a short circuit. And then RB. So I have written RC just for the sake of writing down the equations. Okay. And this is your emitter resistor RE. Okay, so this is the base terminal, emitter terminal, and this is the collector terminal. Okay, so here we are going to connect the source. Okay, the source is Vs, upper side positive, lower side negative. Okay, and between base and ground, the effective voltage Vi is getting applied. Okay, and between emitter and ground, the output voltage V0 is observed. Okay, V0 is observed. Now remember one thing: in case of emitter follower, you see that emitter terminal is common to input circuit as well as output circuit. Therefore, on the input side, if you look at, there is a voltage which is common to the input side as well as output side. So basically the voltage across RE serves as the output voltage V0 as well as the feedback voltage VF. Okay, so you can write that here VF is equal to V0. Therefore, the feedback factor beta Therefore, the feedback factor beta is defined as the output signal to the input signal, right? Input signal. So output signal is VF and the input signal is V0. Both VF and V0 are the same, so beta is equal to 1. So that means to say 100% of the output is fed back an input. 100% of the output is fed back as an input to the amplifier. Okay. So this is an example for voltage series feedback. Okay. And the voltage gain EAV is defined as ratio of output voltage to the source voltage. Okay. Source voltage, which is equal to output voltage in terms of H parameters. You know, the output voltage can be written as HFE IB into RE. Okay, so V0, this is V0, right? V0 is what basically? I0 into RE, which is equal to, what is I0? I0 is basically 1 plus HFE times IB into RE. So in short, you know, 1 plus HFE can be written as HFE into IB into RE divided by VS. Okay, which is equal to HFE into RE divided by VS. Okay, what I will do, this IB, okay, this IB can be written as source voltage divided by the resistance. So this IB can be written as source voltage divided by the input resistance HIE. Okay, so that gives the voltage gain as HFE RE VS divided by VS into HIE. So VS gets cancelled and you are left with the voltage gain expression as HFE into RE, okay, divided by HIE. Okay, so this is the expression for the voltage gain. Okay, so therefore the closed loop voltage, okay, the closed loop voltage AF can be given as A divided by 1 plus A beta. Okay, so what is A? A is HFE RE divided by HIE. Okay, the whole numerator gets divided by 1 plus A into beta. Okay, A is nothing but once again HFE RE divided by HIE into A beta, right? So what is A beta? Sorry, beta is 1. So you would get AF as HFE RE, okay, HFE RE, then HIE plus HFE RE, okay, which is close to 1 because HIE plus HFE RE can be approximately written as HFE RE itself, so that, you know, numerator term is going to cancel out with the denominator term. So this is an example for voltage series feedback. Okay, voltage series feedback, important. Boylsted book.